Probably you remember that we had lost Nurit Shai, but she showed up again, thank God. And so after drones, airplanes, cars, let's go back to bacteria, to an artist socializing with bacteria. Nurit Shai. Thank you.
Oh, hello. Okay. Hi, Roma. First, thank you for Ricardo and Massimo for inviting me here, and for all the staff and team for the hard work and organization. And it's interesting that I'm actually, after all the cars and vehicles, thinking about network systems in nature and what can we learn from nature when we think about designing our future transportation systems, railroad systems for vehicles, but also our mobile phones. Because after all, nature has billions of years of experience. So I'm sorry I'm a little bit jet-lagged, but I've heard that pizza bianco is a solution for everything in Roma. Okay. So never before have we communicated with each other on such mass scale as we do today with the internet. So how do we communicate with each other? Some of you might be familiar with these beautiful data visualization graphs done by artists, programmers, analysts. And today we can tag and track data in real time via Facebook and Twitter. And we're trying to make sense of all this information and all these connections between us. But in fact, some research show that shared data stopped as 93% at the first node itself. On this Petri plate dish, there's billions of bacteria. There's 10 times more bacteria than all population on Earth on this plate. Yet they communicate and coordinate their actions together. How do they do that? But before we talk about bacterial communication, I want to introduce you to 3 very smart bacteria I'm working with. The Panibacillus vortex, which is in the center, the Dendriformis C on the left, and the T. Sorry, left and right. Opposite. So these bacteria found about 20 years ago by Professor Eshel Ben Yaakov from Tel Aviv University are considered to be among the smartest bacteria, scoring the highest bacterial IQ. So you might ask, what is bacterial IQ? And how do you actually measure bacterial IQ? So we actually measure bacterial IQ based on their cooperative collections and decision-making as a colony. So you have to remember that bacteria is actually a singular cell organism, but they work here as a super multi-cellular organism, you might say. And we know that today, that bacteria talks to each other, sending chemical signals that Professor Eshel Ben Yaakov calls chemical twitting. With task distribution, like social insects, some bacteria in the colony would path transport and communication systems, while others would search for food. So when given harsh environmental settings by scientists, so for example, when they're giving hard agar surface growth with very little nutrients, the bacteria is faced with a dilemma. On one hand, they want to maximize the surface to search for food, but then on the other hand, they don't want to reproduce too much so they don't have to share food with everyone in the colony. Known with very advanced social behavior, they develop complex architecture structures that you could see here. What fascinates me eventually, apart from their advanced social behaviors and morphological abilities, apart from these beautiful patterns and advanced architecture structure, is the fact that these could be seen as visual representations for communication systems. A map, a language, a message. So inspired by his research of social life of bacteria, I met Professor Eshel Ben-Yaakov about 4 years ago at Tel Aviv University, and with his generosity and openness to art-science collaborations, he invited me to his lab, and I was trained by his team and came back since every year. As a co-founder of GenSpace, a citizen science biotech lab in Brooklyn, I was able to bring my research to New York and expand on the notion of the lab as my studio. I was able to continue my work with like-minded peers as my co-founders at GenSpace, who were too interested in open science through both practices and hand-on experience, but also through building a community around these notions. So when I come to the lab, I come as an artist, open-minded, with sometimes questions that might be irrelevant or too obvious to scientists. And I tend to come to look at rather than to look for. And I would ask really simple and sometimes silly questions like, why is the agar plate the size it is? Or why do we actually apply flat agar surfaces? Or why do we actually rely on visual observations? Can we listen to bacteria? Can we codify, track, and analyze the signals that they're sending us? So this is an early experiment I did where I was trying to test how bacteria would react to different sizes of Petri dishes. And as you can see on the top row, I used smaller plates with 6 centimeter diameter. And on the bottom row, I used, in this case, a standard plate of 10 centimeter in diameter. And as I was taught by my mentors, I seeded the bacteria at the center of the plate and let it grow. I came back after a few days, and this is what I saw. I was amazed to see how, on the smaller plates, they very carefully forge very, very thin and small arms to scout the surface, while on the larger plates, they felt carefree, forging larger arms, faster speed, with more bacteria, as if they understood the space from the beginning, as if they understood how much food resources they had on the plates. Almost like having a GPS or spies. They didn't wait to reach the edge of the plate to think, oh, we don't have any food left, let's change our behavior. They planned in advance their journey, taking decisions as a colony. Do they have sensors? Did they send spies in advance to understand what's waiting for them? How did they communicate with each other to reach these results? On another experiment, I wanted to further explore the agar. So the agar is like gelatin. When it's hot, it's liquid, like jello, and when it cools down, it solidifies. So I wanted to use this techniques of molding as it would take the shape of the mold itself, and to see if it understands spatial, relationships in morphological? Does it understand space? Would it understand gravity? Or how would it understand different surfaces and landscapes? So I seated the bacteria on these three-dimensional surfaces, and I was really amazed with the results. It was sliding down slopes and climbing up steep and sharp angles. It really understood shape. It recognized the space around it, and definitely created decision-making as a result of that. So I took my experiments further to see how it would understand various surfaces of agar and use the same techniques. I placed my plates on speakers while the agar was still warm and let it solidify while I applied different sound frequencies to the agar, creating various topographies fixed in time. I then later invited some friends and some sound artists into the lab to explore more these sound experiments. And as these sound experiments become more complex, we took it into the gallery space. So I was really interested to share my experiments with the public. So these are experiments that are usually done in closed lab doors, and as a DIY bio advocate, I really wanted to create access and enable the public to see lab work that otherwise they wouldn't have access to. But I also wanted to expand on my own inquiries into experiments that otherwise would not be able to do outside of the lab. So these are some of the results. And you can see clearly here that, for example, with the vortex, which is in the top left and the bottom right, that the top left is with a triangle wave and 200 hertz, and in this one is a square wave with 1,000 hertz. Creates completely different patterns and morphologies. Something else really interesting happened here. So the C and the T, as you saw before, are closer species in the bacterial kingdom, you might say. And usually when you put one on the favorite agar nutrition food of the other, it would change and imitate the morphologies of the other bacteria. But what happened here, and you can see it on this plate here, on this plate here, is that the wavy surfaces created change in the morphologies back and forth with the C and the T. So when I took it back to the lab and showed it to the scientists, they wanted to further explore these phenomena. When I showed them the 3D experiments I earlier did, they were interested in the results too, which for the first time as an artist I felt useful at the lab, not only taking, but maybe, hopefully in the future, giving back. And then something else interesting happened. So usually scientists would grow the bacteria in an incubator with 37 degrees Celsius. But because I'm working a lot in galleries and museums, I like to imitate and simulate my conditions, and I grow it in room temperature or in colder conditions. So one time I decided to speed the process and put my bacteria into the incubator, and I came after a few days and I saw this, the blurb. I was so disappointed, and I thought, this is not a social bacteria. They don't know how to communicate with each other. They have Asperger's. I was very disappointed. So I slept over it a few days, and I thought about what happened in this plate. And then I realized that, in fact, they were having fun. They were warm and fuzzy, and they had plenty of food, so they didn't make any effort. And then I went back into my three-dimensional experiments. And you could see it clearly here, that when they had to struggle with their surface, they were more creative. They were more innovative. And then I thought, What does it mean about us? What can we learn from this? When are we more creative? Is it only in times of stress? Is it only in time of struggle, in war? And what's the relationship between creativity and problem solving? Or in this case, of beauty? Is it when we recognize beauty in nature? What is in us that actually tells us what beauty is or what creativity is? Is it that when we recognize mathematical patterns, complex networks, systems in nature, that we regard it as something beautiful? So these are some of the close-ups of my plates. And this is just one project that is done at GenSpace, a citizen science biolab. And I do hope that in the future, many other artists, technologists, architects, programmers, designers, anyone, citizen, could come and tap into lab work, science, art, technology, when we're thinking about the title of Maker Faire is Making the Future, right? And take responsibility and take part in the dialogue and be critical about how we are going to shape our future and what we can learn from nature and its creativity. So I'm going to end with this slide with some of GenSpace members' projects. And thank you.
Thank you.